Uh, okay. Hi, everyone. Thanks for coming. My name's Nick. I'm a research fellow at the School of Psychology. And for some context, I've been working for the past year and a half or so with Charlotte Ray here, also from psychology, on how to measure and reduce the carbon footprint of research computing. We've been working specifically in the area of human neuroimaging. That's kind of our background. But today this is the culmination of this work today. We're sort of zooming out and focusing more generally, how can you reduce the carbon footprint of your own computing? And just as a bit of context, we don't often think about the carbon footprint of this element of our work, but there is one. Anytime that we press go on analysis, anytime we run something through a computer that is using energy, which in turn has a carbon footprint. And estimates vary pretty wildly on this, but it's believed that carbon emissions are somewhere in the region of 1 to 4% of global CO2 emissions when we consider the IT sector and sort of data centers as a whole globally, which sounds like a pretty small number, but it's large, and we consider that this might outweigh the contribution of industries like aviation and shipping, which are around 2.5% of global emissions. And there's obviously, in recent years and in the coming years, there's ways this has changed and will continue to change. So we've seen advances in hardware, meaning computing is becoming more efficient and we can do effectively more for less or for the same amount. But what we're concerned about here is this idea of a rebound effect, where effectively resources becoming cheaper and more available mean we end up using more overall rather than less. Yeah. And we'll talk more about this in detail later. I'll just say as well, please feel free to raise your hand or shout out at any point as we go through and ask questions. Very happy to stop down at any point. So the emissions that come from this sector arise from a couple of different sources. So first, we consider the actual storage of data. I know this might, again, it's not intuitive, but storing data on servers itself has a carbon footprint. The more data we're storing, the more we need to actively back up, the more overheads we have in terms of air conditioning and things like this. And just need more kind of base energy to run those servers. Maybe more importantly, though, the faster that we fill servers up with data, the more frequently we need to buy new servers in to replace or supplement them, which has this sort of embodied footprint, which is much larger than the cost of actually storing data itself. And again, there's no perfect estimate for this, but it's believed that the footprint of storing data is roughly 10 kilograms of carbon for each terabyte of data that we store per year. So again, it's kind of the longer that we store the data, the larger a footprint we have. And this becomes, especially under a problem under these circumstances here. So there's this idea of dark data, which is effectively when we have data that sits on a server and is poorly indexed and poorly documented. So it might be a postdoc who comes to a lab, works on this data, leaves it on a server without really explaining to anyone what it is before they leave. And in that case, we end up with data that no one's confident enough to delete because they're worried it's something important, but equally no one can make any use of either. It becomes functionally invisible over time. So in this case, we just end up with exponentially more and more data that's serving no purpose, basically. Even for the data that we do want to keep and that we plan to keep, a big chunk of this will be what we consider junk data as well. So we might run stuff through a pipeline and generate a load of data, including sort of intermediate working directory files, which ultimately we're not going to use, no one's ever going to use. So having good data management plans in place for how and when files are going to be deleted helps to avoid this problem as well. And again, we'll talk later about some specific ways to sort of clean up your digital junk. We work specifically with this tool, fMRI Prep Cleanup, which is a tool used in human neuroimaging for processing data. This tool has been a big part of our work as we've considered the sustainability of computing. Again, I'll touch on this more later, but this package combines best practice tools from a number of different sources. So it's considered as being sort of best practice in the field by many, but it's also quite computationally expensive and can produce large amounts of data. And when we initially used it, one subject produced just over 5 gigabytes of data. After combing through and doing a bit of an audit, we found that for each subject, about 96% of that could be considered junk by our definition in terms of we were never going to use it again in any analysis. So we developed this tool, fMRI Prep Cleanup, which can automatically comb over this kind of standardized output of this program and delete that junk data, just leaving you with what you're realistically going to need going forward. This is obviously very discipline specific, but hopefully it's a good example of how it's fairly easy to develop these tools to sort of do similar things for other tools in different disciplines. And there's often some low-hanging fruit here. So this, this amounts to 1.3 terabytes of data being saved over the span of our sample, which is about 250 subjects. So this adds up pretty quickly. Other newer imagers in the room may have worked with SVM before as well. This is a different data processing tool. The footprint here in the data generated is much lower. It's around 0.6 gigabytes per person. But again, we've generated this tool, SVM Cleanup, very recently, which can do the same job, basically deleting files we consider junk, which is about half, which adds up over time, over a large sample, to 70 gigabytes in our case. So that's a pretty sizable there as well. So that's data storage, but we also need to think about the footprint of data processing, which has been kind of the focus of our work over the last year and a half. And effectively, the idea here is that the longer that we're asking a computer to run a given job, the more we're having it do, the more energy it's using, the larger a carbon footprint it has. And if we can find ways to reduce the time that those CPUs or GPUs are spent running, then we can kind of proportionally reduce our carbon footprint. And part of this is just the efficiency of programming, because again, if we've written sloppy code that involves kind of loops within loops within loops that are doing maybe redundant things over and over again over many iterations, this ends up adding up to a lot more time on the part of the script running, which is bad for its energy use, and also it's bad for your own use as well in terms of having to wait longer to get the results that you need. And even if we're making only small savings by kind of brushing up on our coding over a given loop, again, over many iterations, this can add up to a lot of energy and a lot of carbon. This is a paper from 2021, focusing on the relative energy efficiency of different programming languages, as well as the time they take to do the same job. And I've highlighted Python here because this is pretty striking. I'm not sure about others in the room, but this is the primary language that I use. And according to this paper, it's massively energy inefficient when we compare it to things like C and Rust. So again, here, just your choice of programming language is going to end up affecting things like your energy use as well. There are packages like NumPy you might use in Python, which might kind of wrap in other languages, which mean that the kind of overall your footprint might not be that bad, or your efficiency, sorry. But kind of base Python is pretty energy inefficient, as it turns out. Yes. If I had to guess, I would say it's the older language are working with more limited resources when they were built, would be my guess. This is kind of an example of the rebound effect, if that is what's happening, that languages that have come along later are just able to make use of more resources, basically, and make use of them without, like you said,
even if they don't need them.
Yeah. I'm really not the expert on the efficiency of programming, but if you are interested in learning more about this, we ran a conference last year, the environmental impacts of computing, and our colleague, Lincoln Colling, who used to be here at Sussex, gave this talk, about 15-minute talk on the efficiency of programming that you can find on YouTube, along with all the other talks from that workshop. He goes into a lot more detail at specifically how you can edit your code to kind of take out these redundant loops and things like this. So do check that out if you're interested. So luckily, we can estimate the energy usage from our computing. And to do this, we need a couple different components. So first, we need to measure the energy usage that are happening from CPUs that are actively running on a job. And so the broad formula for this, which is generally pretty well accepted, is CPU time, so the amount of time that CPUs are actively performing that job, times by the thermal design power, which is sort of like the heat wastage that comes off of a given processor. It can be kind of taken as a proxy of its energy efficiency, divided by the number of CPUs that you're using. So you might spread a job across 4 or 5 CPUs, for instance, or just be using a single one. So this formula is kind of considered fairly uncontroversial in terms of it's been validated as giving a fairly accurate estimate of energy usage for CPUs. We also need to add this to the energy usage for RAM, random access memory. And this is a slightly more contentious formula. We've gone back and forth with collaborators on the perfect way to do this. But what we've landed on and what other tools have used is the maximum memory used at any point during a given job. It could be 8 or 9 gigabytes or whatever that might be, times by the volatile memory consumption, which is kind of a static factor that you apply to each calculation, and then the runtime of that job, basically just how long it took to complete. So we add CPU and RAM energy usage together, and this varies depending on the hardware you're using, but CPU tends to account for around 70% of energy usage and RAM for around 30%, generally speaking. So yeah, from that, we can get a fairly accurate estimate of our energy usage. But just knowing the energy usage of CPU and RAM isn't enough. We need to put that in the context of power use effectiveness. which basically considers the energy overheads needed to run that computing. So as well as the actual processors doing what they need to do, we need to consider the lighting and the air conditioning and various other things that are needed to also operate a data center. So basically, the lower a number we have here, the more efficient our computing is. So, or the overheads are. Sussex, as of at least November 2023, has a PUE about 1.28, which is good when you consider the industry standard is 1.55, so a fair bit higher. And what this effectively means is that for each kilowatt hour of energy we use directly for computing, we're using 0.28 for those overheads. So at the moment, Sussex is doing pretty well, to be honest, in terms of this figure. As we'll see later, this is likely to change, though, in the near future. We also need to consider energy from RAM and CPU times what power use effectiveness gives us the overall energy usage for our computing job. We also need to consider this in the context of carbon intensity to get our estimate of actual carbon emissions. And this is basically for each kilowatt hour of energy that we use, how many grams of carbon are we emitting? And this is lower when we're using more renewable energy sources or low carbon energy sources, and higher when we're relying more on things like natural gas and coal. And luckily for us, we can get live data from the UK that shows us an estimate and a forecast of what the overall carbon intensity is for the UK as a whole and in different regions of the UK that we can make use of here. And this is data from that live API from a recent paper of ours. On the y-axis here, we've got carbon intensity in grams, kind of average carbon intensity. And on the x-axis, we've got for a given day of the week, for a given time of that day, what's the average carbon intensity? So for instance, we've got the average in carbon intensity on a given 8 a.m. on a Tuesday in 2018, for instance. And what we can see here is fairly predictable patterns throughout the day where intensity tends to peak at the start and the end of the working day when overall usage is highest, and then to be lowest in the middle of the working day, overnight, and particularly at the weekend when that usage kind of dips down. And that's because when energy usage is higher, we can use the more desirable sources like wind and nuclear. And when it's when energy usage is higher, we have to rely more on less desirable sources like natural gas. So we can make use of this information because we can know that if we submit a job on Saturday morning rather than on Friday night, we're likely to be able to use the same amount of energy for less carbon, potentially 30 to 40% less carbon sometimes, or even more. The other nice takeaway here is you can see that year on year, so the darker the lines get, the further on in time we go, the UK is gradually decreasing in carbon intensity, or for one period, fairly rapidly as we adopt more and more renewable energy, which is great to see, and hopefully we'll see that continue in the coming years as well. Carbon intensity doesn't only vary by time, but also by location. So again, on the x-axis here, we've got our carbon intensity in grams. And on the left, we've got different countries across the world, and on the right, different US states. So we can see that the carbon intensity of South Africa is much, much, much higher than that of Iceland. So South Africa relies primarily on coal, Iceland primarily on geothermal energy, or France, for instance, down here at the bottom on nuclear energy. You see the UK, I think, somewhere down here in the green. Same for US states. So we can see the carbon intensity of Wyoming is substantially higher than that of other states like Washington and Vermont. Obviously, this information is slightly harder for us to use than time, because often we'll be using servers that are tied to physical locations, like the ones here at Sussex. We can most easily make use of this information when we're choosing between cloud computing services that might be based, for instance, in Canada, that relies largely on hydroelectric energy versus the US, which has much higher carbon intensity. So effectively, where we're choosing to store our data by cloud computing services. There is kind of a social implication to this as well, because this means that we may be prioritizing more privileged economies with access to these renewable resources and at the cost of countries that maybe don't have the privilege yet of renewable energy. I'm not saying not to use this information. That's just a caveat that we've discussed in our papers, the fact there is sometimes a bit of a trade-off here. But yeah, so we can use both the time and location of our computing to influence the carbon intensity, so effectively how much carbon we end up emitting for the energy that we use. So then we can get our overall estimate of carbon emissions by multiplying our overall computing energy use times our power use effectiveness times our carbon intensity, which gives us a number in grams or in kilograms, if we convert it, of how much carbon we've emitted. That'll always be an estimate, but again, hopefully with these different factors, it should be fairly representative. No, yeah, we've considered it to do the platforms like the Open Science Framework, or for us, it's platforms like Open Neuro for storing neuroimaging data. Yeah, as with the storage of kind of local data, that cloud computing still has a carbon footprint. So we've had conversations recently around kind of tensions between open science and sustainability. This idea that if we're exponentially just putting more and more data online, which is what we're doing at the moment, effectively, eventually it's going to become unsustainable just financially for the platforms hosting it as well as kind of environmentally. So yeah, we discussed whether it'd be useful to have kind of conventions about deciding within a given discipline, what do we realistically need to share? Maybe that a lot of people are sharing data that it's good practice to share, but realistically it's never going to be used. Whether that's having some sort of like expiration or archiving date on that data that goes to cloud computing services, maybe, or just having better conventions about what we do and don't share. We're not sure. Yeah, this has been kind of like a controversial topic for us in neuroimaging at least. So, but there definitely is a footprint there. We don't kind of have good estimates of the magnitude of it. Okay. So that's the kind of the broad formula that's used for carbon tracking. There are several different types of carbon trackers. Broadly, we've got online calculators, embedded packages, and server-side tools. And in the second part of this workshop, we'll provide some kind of hands-on demonstrations of those tools. I won't go into all the advantages and disadvantages of these packages or these approaches now, but they do have upsides and downsides in terms of flexibility and ease of use, and kind of generalizability. And it's worth checking out this paper from 2023 if you're interested in learning more about those. We'll talk about green algorithms later, which is an online calculator. So here you can basically manually input factors like duration, number of processes, type of processes, and it will spit out an estimate of carbon emissions at the end. But yeah, we'll practice using this tool later. Code Carbon is an example of an embedded package. And what this basically means is that you've taken a tool, an existing carbon tracking tool, and built it directly into an existing program. And for us, again, that's been this tool, fMRI Prep. So you can just toggle on this track carbon option in the command line, say where you are in the world, and it will spit out at the end for each subject what's the estimated carbon footprint of that pre-processing, which is a great idea intuitively, because it means that users don't have to do any extra work at the start to set those tools up. It sort of just automatically happens and it's built into the tool in a way that's kind of the perfect scenario. But I wanted to get a bit of a cautionary tale from our own usage of this tool. So we, as I'll talk about soon, we ran a study where we submitted basically the same job for 250 subjects and looked at the carbon footprint of each of them. And on the y-axis here, for both graphs, we've got the estimated carbon emissions. On the x-axis is just the order in which we sent them to the high-performance cluster here. So basically the time at which they were submitted. They kind of went in little groups. And what we saw with Code Carbon at the top is that we were having these systematic bumps in emissions. So between like an 8-hour period, suddenly we'd have these very high estimates, and then it would sort of calm down again and come back to sort of a bit of a flat, which makes no sense at all, because the jobs we're submitting to the cluster should have their own dedicated resources. They shouldn't be influenced by other jobs, both kind of our other fMRI Prep jobs, but also other jobs happening at the university. Reese here in the computing team developed this server-side tool, which instead of running at the time of pre-processing, uses high-performance computing logs that are specific to that job to kind of pull out an estimate afterwards. So we use that new tool on the exact same task that we'd run, and we've got that data on the bottom here. And what you can see first is that these systematic bumps disappear. We had more of a flat line across our different subjects, but also that the estimate of carbon emissions is only 10 to 15% that it was with Code Carbon. And what we basically figured out here was that Code Carbon wasn't just telling us the carbon emissions of a given participant, it was telling us the carbon emissions of the entire node. So there might be 4 different subjects running on the same node. We might be sharing a node with a particle physics simulation or something really energy hungry. So it was taking account of all of that, but also the kind of baseline energy usage of the node, which was really not what we wanted. We were getting a lot of information that wasn't useful to us there, and basically a confound in our design. The benefit of the high-performance computing logs method at the bottom, which Reese helped us develop, is that it's looking directly at the job that we've run and getting the energy usage from that. So embedded tools, you think, are probably still useful, but probably best when you've got hardware isolation. So basically when your computer is doing nothing but running that task. Otherwise, it becomes a bit tricky to kind of disentangle exactly what it is that you're measuring. And I'll talk more about our server-side tool later as well in the second part of the session. Okay, so I'm now going to talk about some research that Charlotte and I ran, some case studies basically on reducing use of computing in neuroimaging. So the first study we ran was measuring and reducing the carbon footprint of this tool, fMRI Prep, which I've mentioned several times. So again, this tool combines functions from a bunch of different sources, provides this kind of optimally pre-processed output, and is considered by many as best practice. For this reason, it's also quite computationally expensive, relatively speaking. But for our purposes, it was good because it allows us to add, remove, and kind of vary different pre-processing options in the command line fairly easily. So we can take out or add in different steps, run them for the same subjects, and see what is the difference in estimated carbon emissions, basically, across people. So it was useful for our purposes. And for this, we use existing data stored online. So we had data for 257 subjects who performed one run, so just 5 or 6 minutes of a task where they were either pressing a button with their finger or inhibiting pressing that button. This task was important for us because it produces quite reliable patterns of activation in the brain. So we'd expect the primary motor cortex to light up when people are pressing buttons around here. And we'd expect areas like the primary motor, pre-supplementary motor area to light up when people are inhibiting a button response. And this is important because we wanted to quantify how good a job our pipelines were doing with the data, basically saying that if we had higher evidence of activation in these regions, we could say that the pipeline was producing more robust data. That was kind of the most sensible metric of performance that we could find to weigh against carbon emissions. What we did was run 8 different versions of fMRI Prep. So I won't go over all of them, but we ran all subjects first through a pipeline where settings were largely kept at default, like on a baseline. Then one where we were removing this default step of free surface reconstruction, which is normally just running there, unless you tell it you don't want it to run, basically. One where we're asking it to run in low memory mode, so restricting the resources given to that job. And one where we're increasing the resolution of our output data, among other things. So again, we were just running all data through all 8 of those pipelines and measuring the carbon emissions of each, as well as the performance of each. So here are our results. We've got our carbon emissions in green and our performance in purple and pink. And our baseline one is here in the middle with our kind of experimental pipelines on the sides in order of carbon emissions. So a few kind of broad observations here. We can see that first one, removing surface reconstruction, reduced emissions in our case and duration by about 48% with no loss at all in performance. The output generated was still producing kind of as good quality data as we had from our baseline. Other steps like going to low memory mode reduced emissions by about 6%, again with identical output in this case and no loss in performance. And on the other side, we had steps like increasing the resolution of our output data, which increased emissions by 70% and file size by about 200%. Again, in this case, with no bump in performance, that kind of stayed static. So hopefully what these results show is that you can kind of disentangle the computational resources that are given to a given task and the quality or the usefulness of the data that you get out. And based on these findings, we were able to, well, actually first, so we can take, to make it more concrete, we can take the overall emissions for each of our pipelines and convert this into miles driven in a gasoline-powered car. So a baseline, this was equivalent across all 257 subjects to driving around 19.2 miles from here to Worthing. When we remove surface reconstruction, that drops down to 10 miles from here to Shoreham by Sea. And increasing the resolution of our data goes up to 32.6 miles from here to Bognor Regis. These obviously aren't huge numbers in miles, but we were using a relatively small amount of data. So obviously the more data you're using, these numbers are going to jump up. If you're using, if you're in an area of higher carbon intensity, the actual numbers will be higher. But the overall kind of scale of difference between these different options should remain kind of static. And based on these findings, we're able to make 6 recommendations to people using fMRI Prep, basically saying things like, if you don't need the generated output files, turn off surface reconstruction. It's kind of a no-brainer. You can use things like low memory mode to reduce your resources with no real trade-off to the user as well. And avoid doing things like using high-resolution output data that doesn't appear to give much of a bump in performance. Again, these are all very specific to neuroimaging, these specific recommendations, but we hope this paper serves as a bit of a model for how people in other disciplines can kind of weigh up the benefits of different settings and tools, basically, whether there might be scope for your own computationally expensive tools that you use to reduce emissions without losing anything in the data that's important to you. So we then ran a second study I'll go over quite briefly, which was now looking not just within a given package, but comparing across different neuroimaging data processing packages and seeing what was the different carbon footprint across them. And we looked again at fMRI Prep and compared them to FSL and SPM, which are two slightly older tools that were built, I'm not sure how long ago.
90s.
Yeah, okay. So fMRI Prep kind of includes a couple of tools from FSL and other packages. And so we basically ran, again, the same data for each package, estimated the carbon emissions, and again, looked at the performance of each. And the differences here were pretty striking. So there was some difference between FSL and SPM. SPM was using about 30% more carbon. But fMRI Prep overall, across pre-processing and statistical analysis, was using about 40 times the carbon that FSL was and about 30 times the carbon that SPM was. This is the difference between maybe 4 hours of computing it for data and maybe 9 or 10 minutes. It was massive, basically. And this is kind of what we expected. We knew that fMRI Prep was pretty computationally expensive. We didn't expect kind of this degree of difference. When we look at our performance measure again, task activation, this time looking in 4 different regions, we can see this varies somewhat by region, but overall, fMRI Prep does do a bit better than the other packages. It produces about 20% higher evidence of statistical activation, which isn't nothing. You know, that's 20% is a pretty good bump. But it's obviously not in line with the bump that we see in carbon emissions. I want to make clear here that we're not sort of demonizing use of high compute tools like fMRI Prep, because producing good quality data is important for worthwhile science. And if we can get better quality data, that's great. We're more just saying, if you are using tools like this, kind of be aware of how you're using them. Consider if there's ways in which you can produce the same output, but use less resources, as well as also signaling to developers that might be scoped to reduce the footprint of their own tools in kind of upgrades that would allow them to come more in line with these older tools. Okay, so I wanted to talk now a bit about more broadly the future of computing and how this might change over the coming years and decades, both within Sussex, but also beyond. So in terms of how things might change, it won't become a surprise to anyone, the increased adoption of machine learning and AI. So this figure here is showing that in all kinds of industries outside of research, we're seeing very regular use of generative AI now. And in neuroimaging and in other research disciplines, the use of machine learning tools as well is starting to balloon and will continue to do so over coming years as well. As you may have heard about, for tools like GPT, the energy needed to train and test these tools is pretty high, and so we're likely to see that as well in developing these tools as well as using them in the future. That's likely to increase the overall energy usage of this element of computing. At the same time, on kind of the other end, as I alluded to earlier, we are seeing these steady upgrades in hardware over time, which mean that we're able to do more work for the same amount of energy, or less energy even. And the kind of the trend of this has been pretty good. This is going back to the 90s and into 2025. Hardware is gradually becoming more efficient at being able to perform these tasks. And hopefully, whether this rate of improvement will continue is another question, but hopefully we'll see hardware continue to improve, which will be good for energy efficiency. Another piece of this picture is increased centralization. And we kind of alluded to this earlier with the sharing of data online. It tends to be that we have large data centers, like those run by Google and Amazon Web Services, who tend to host a lot of data online, have fairly good power use effectiveness. They've got these kind of like highly efficient systems of servers where they've got good infrastructure, basically, which allows them to air condition and operate these servers in a way that might be more efficient than smaller, less local data centers. So increased use of these larger data centers might lead to overall kind of increased efficiency of energy use of computing. The downside is this often means we end up relying on large tech companies. So platforms like Google and Amazon will at least claim to be using 100% renewable energy or aiming to use 100% renewable energy. But researchers may not always feel comfortable in trusting data to these corporations, particularly as we go forward into the future. There are alternatives on the horizon. The EU's high-performance computing joint undertaking is a new initiative that basically provides these highly centralized large data centers without having to rely on tech companies. So that will be an option for storing data in the future, but something to consider. We've already talked as well about decarbonisation of energy. This is again data from the live UK carbon intensity API. And we look across each year on average, we are seeing pretty good drops according to these figures in carbon intensity year by year. And we hope that as the next few years go on, we'll adopt more and more renewable energy, and these numbers will continue to drop, which means we can use the same amount of energy for less carbon. Obviously, it's an open question about whether this trend will continue, and in many places in the world, this trend is not happening to the same extent. We also need to consider that in any case, infrastructure for renewable energy is limited. So even if we have 100% renewable energy, if we use exponentially more and more energy, we'll eventually outpace our ability to use that renewable infrastructure. So we still can't go too crazy with energy use here. Yeah, and carbon intensity is not the same as carbon emissions, I guess, as well. We can continue lowering this number of using more and more energy. That number will still continue to rise, which is really what matters. So all of this kind of compounds into, I alluded to earlier, this idea of a rebound effect, which is effectively as things become cheap and more efficient, we don't use less, we end up using more in some cases. So in this example here, if the fuel used to power our cars becomes more energy efficient, this has direct savings. We might use less energy to power that car. But at the same time, maybe that will mean we have lower petrol bills, which means we save some money, which means we end up taking more holidays to Spain, which are relatively cheap, leading to this indirect increase in energy usage. Maybe as well, because our car's got lower running costs, we actually end up using it more for more frequent and for longer journeys, and again, leading to indirect increases. So in this case, indirect increases in energy use end up outweighing the direct decreases. And this is similar to what we're considering with computing here, as we've seen in the last few slides. So again, even though there are improvements, we can't kind of take our eye off the ball here. So I'll talk now about the future of high-performance computing specifically at Sussex. Well, not all of this is fact as far as I know, but this is kind of the picture that I've been painted so far. So as many of you may have heard, very soon Sussex will be moving from its current high-performance computing system, Apollo 2, to Artemis, which I believe will be coming in July in early stages, which will come with several changes. So first, we'll be switching from the current scheduler, which is Sun Grid Engine, to Slurm. Which is kind of good for our purposes. It means that we'll be able to integrate more. Slurm is a much more common scheduler at different institutions. We'll be able to integrate green computing tools basically built for other systems that we can just plug into ours and hopefully give access to users across the university. I've been told as well that nodes will be powered off when they're not in use now, which is great. It means we'll have less kind of idle wastage of energy. I've also been told that the average emissions from a single job on a CPU processor might drop drastically, just with, again, upgrades in hardware that will be coming in, which again is great. That said, power use effectiveness is likely to get worse, right? The system's actually becoming more dense is the way it's been described to me. So we're packing in more computers without necessarily the infrastructure yet to support them. So overall, kind of overheads might end up being worse for that overall. We're also going to have increased use of GPUs, graphical processing units. We've only had a couple before, more are going to be coming in. And these are inherently harder to make power efficient, energy efficient than CPUs are. So we're likely to see increased energy usage from this element of the system as well. And finally, because of this increased flexibility, it's likely that the system is going to be used for a wider variety of tasks than the previous Apollo 2 system was, which is really like a perfect encapsulation of that rebound effect. So if we consider all of this together, even though certain things are becoming more efficient, it's likely that energy use is going to increase when we go to this new system. So yeah, again, this is information that I've been given so far. How much of this will come to pass, we'll see. But hopefully when the new system comes in sometime next year, probably we'll have more workshops focusing on specific use of tools on that system. So do keep an eye out for that. So that's the end of this first session. We're going to take a lunch break now for about half an hour and come back at 1:10, at which point we'll be doing some kind of interactive tools demonstrations. Before we stop down, are any last questions or comments before we stop for lunch? Yeah, for sure. And that's an important point. We don't want to have people focusing on spending lots of time basically on stuff that isn't going to matter that much. And it's true that if you're running a job that's going to take 5 minutes rather than 10 minutes once, maybe it's not worth your energy to spend that much time optimizing it. Or if you're considering like the storage of Word documents or PDFs, again, we don't want to demonize that too much. It's always good to clean up junk. It's, again, the less energy you're using, the better. But it's kind of best to focus on cases where you're using high performance computing, or even when you're not, if you're running tasks that are going to last for hours or days. At that point, I think we say that. I mean, I'm not going to give you like a cut-off number. I don't have that for when it starts being important. But Yeah, and there are cases there where even like leaving sessions logged in on the neuroscience system, you've seen how like when the system slowed down before, it's because we've been having lots of like versions of MATLAB just running in the background, just keeping logins there basically, which that has an energy use as well. So I don't know. It's hard to give like a cutoff for when it starts mattering. But I guess if you're using resources that you don't need to use a tool basically and can avoid, that's always a good thing, particularly when it's something high performance or running over a long period of time is when it starts being kind of high impact, I would say. It's true, yeah. So in terms of like the embodied footprint from like producing and manufacturing and transporting servers and computers ends up being like a large chunk of their overall life cycle. It's true. So the more we can do to kind of to lessen that basically by reusing all the systems, by not replacing servers when we don't need to, by holding onto laptops as long as we can. It's kind of it's a different practice, I guess, but it's like a really important part of the picture, I think, in terms of I can't remember percent off the top of my head, but the energy needed to actually produce these materials often ends up being more than the kind of life cycle energy usage of them for computing, if that makes sense. Yeah, so I haven't worked at the EEG myself. My instinct is the footprint is quite a lot lower than fMRI. I don't know, to be honest. There's not actually been any research specifically on this topic. Charlotte, I'm not sure if you have any instincts.
If you can do it on your computer and it takes like, say, 5 minutes per person, then that's going to be quite a lot smaller than what we've been talking about, particularly with the fMRI practice. Yeah. So if you're running it on your computer and you get it done in an afternoon for your whole study, I wouldn't buy it.
Okay. Thank you everyone for not leaving, for sticking around. So we'll start back up now. In the second half, we're going to do kind of a more interactive focus on use of green computing tools of a few different kinds. We'll work through each of them in turn. Okay, so we're going to start looking at data cleanup. We've talked about this a few times today already. Effectively, we can reduce the amount of sort of junk data that we're keeping on servers. We can reduce the energy cost of storing that data, as well as reducing the need to buy in new servers to replace them. I've talked about the tool fMRI Prep Cleanup that we've created. What I'm going to do first is just run through a couple-minute video, just running kind of an example of how I've used this tool. Obviously, this is very specific to the one tool that we've used, but I want to kind of present this as a bit of a case study for how you might develop tools in your own field for your own programs that you use to achieve similar things. So first, you can see here, I'm just looking at the amount of data we've generated for one subject. So we just start off by checking how much data we've actually generated. Takes a couple seconds to come through, but ultimately what we've done here is generated 5.8 gigabytes of data for this one subject, which over our 257 subjects add up to over a terabyte, so quite a lot. And this includes the data that we want from the subject, the kind of pre-processed data that comes out the other end, as well as this massive amount of working directory and temporary files that realistically we're never going to use again. So we've got this Python script that is built specifically for this program that will run through, find data and delete the files that it doesn't think will be needed. So what I'm doing here is I'm calling my fMRI Prep script. I'm telling it I want you to focus on this specific directory with a subject's output, and then I'm giving it a method. And basically what we've done here is we've made multiple modes of the tool. We've got like a delete method where it'll run through and delete files, and a simulation method where instead of deleting files, it will create new folders with symbolic links to all the files it would delete and all the files it would retain. Basically, the idea being it's sort of like a low-risk way to test out exactly what the script would do. And the way this one works, specifically, is to look in the directory that we've given it and delete every file that doesn't contain one of these strings. Because we know for our purposes, these strings should leave us with just the pre-processed data that we're interested in and kind of the report files that we're interested in. Everything else will basically be deleted. So it is, in a way, a kind of a high-risk strategy, which is why we put these warnings on it, saying be careful, and is why we provide the simulation mode as well. But here I've chosen the simulation link mode. So in this case, nothing's actually going to be deleted. It will just kind of simulate what would happen. Once it's selected, it will take a few seconds for it to get going, but then it'll start running through these files, create these new folders with a retained subfolder and a deleted subfolder, depending on what we're keeping and what we're getting rid of. And like I said, we've made one of these for SPM as well. This other tool that you can access as well on GitHub. So now this is the kind of the simulated folder created. You can see we've got this retain subfolder. That's everything we keep. Deleted subfolder. This way you can go into it and make sure you haven't got like your entire home directory in there or something, or like all these analysis files that you wanted to keep. But that all looks fine in this case. So now I'm ready to delete these files. I'm confident that I've targeted the right directory. So I'm going again into that same folder. I'm calling the same script, fmri cleanup, pointing at the exact same directory. And then I'm going to tell that I want to use the delete method this time, so it'll actually get rid of these files. And this time we get a much more scary warning saying you're in deletion mode. These files are going to be deleted. Make sure this is exactly what you want to do before you continue. And we've got on the GitHub as well a little sort of like promotional video that runs through exactly how the script works and provides all the different definitions of the flags that we use. There it goes, deleting the data. So we'll jump forward in time again in a sec, and we can check what that's done to our output folder. So again, previously we had 5.8 gigabytes of data. Now here we can see we've got just the pre-processed data that we're interested in. All the working directory files are gone. And we check the file size now. It's dropped down from 5.8 gigabytes to just under 300 megabytes. So a pretty massive reduction, and we haven't lost anything important to us. Again, this is a very specific use case, but we just want to present this kind of an example of how you could think about tidying up your own data, whether that's through automated tools like this or just manually figuring out what it is that you need to keep and delete. This is a valuable thing to do. So what we'll ask you to do now is just to take 5-10 minutes. We'll see how long that takes to look at some of your own data, if you have it on your computers, and think about what you could clean up. Basically, are there files that you need to keep, files you don't need to keep? Just try and get a rough idea of whether there is kind of an extent of wastage there. If you don't have access to your own data right now, feel free just to chat with others in your table about how you'd feel about deleting data. Do parts of this, does the idea of it scare you in some way? Do you kind of not want to get rid of stuff that you might need later? Just have this general conversation. We're not going to encourage anyone to actually delete anything in this session, just for the sake of safety. Have a think about it now, and that can be kind of your homework to take away. But yeah, we'll come back in around 5 to 10 minutes if everyone wants to, to make a start on that. So we're going to move on to now to carbon tracking. And we've talked about several different ways that you can carbon track. We're going to start just by looking at this online calculator, Green Algorithms. And this is maybe the most immediately accessible way to track carbon emissions. It doesn't require anything that's being set up beforehand. So the URL will be on various slides here, but if you make your way to this website, you can access the calculator yourself, or if you just type in Green Algorithms calculator into Google, it should pop up. And effectively what you have is something like this. Well, you have this, which is a bunch of boxes where you can input parameters here. You can do something like runtime, the type of cores you've used, so CPU or GPU, the number of cores that you've used, your location, and various other things. And it will spit out at the end just an estimate of energy usage and carbon emissions. So for the next little activity, if you could use this information here on the screen, just to put in your own little numbers of how long the job will take, the processor you're using, all these various things, and just see what comes out the other side in terms of carbon emissions. Or if you have parameters that are more relevant to your own work that you're running, if you know that your thing takes 6 hours or 8 hours to run, feel free to use that number. But just try and see this kind of carbon estimation process through to the end, to the point where it will give you an estimate of carbon emissions. And just let me know if anything on there is confusing. So hopefully everyone got through to a final estimate, which would have looked something like this. So for the parameters that I had, it gave me an estimate of about 15 grams of carbon, so that many watts of energy. And it will tell you as well the equivalence in 3 months sequestration, as well as distance gone in a car and percentage of a London to Paris flight. So the benefit, it'll also tell you hopefully the distribution of energy across CPU and RAM, which again in this case was about 70 CPU, 30% memory, as well as how that would change in different countries at different carbon intensities. So the benefits of these tools is that they're effectively like, you don't need to have any prior setup done to use them. You can just access them immediately. but they do require kind of manual interfacing, which is not so ideal. So the tool that we'll talk about next is called CalcCarbon. Oh, we've already done that. CalcCarbon is a tool developed here at Sussex. I mentioned it. It's the server-side tool that we developed with Reese in the computing team, which basically, rather than you having to manually input stuff into a website, it grabs information from the high-performance computing logs and then gives you an estimate of carbon emissions after the fact. We're not going to have people use it here in the room because it's been built specifically for the Apollo 2 system running at the moment, which will soon become redundant when the new Artemis system comes in July. I think Apollo 2 will be kind of deactivated in October, November time. But what I'll do is I'm going to show you a brief video of how this works conceptually, because we'll have similar tools coming along that are built for the new system in the future, hopefully. So this here is just a script that I would use to pre-process fMRI data. It doesn't matter specifically what it is, but it's set up. So we're going to run the same exact task for 3 different subjects using a tool called FSL. We're going to pre-process some data. So here I'm on the Apollo 2 high performance kind of cluster interface. And all I'm doing to start is just finding that script and then submitting it to the cluster, at which point it's going to go onto one of their nodes, run kind of automatically in the background, and then it will finish and we'll have the files there that we can access and use. So here's me just submitting that job, FSL pre-proc. It'll take a couple of seconds, but eventually it'll enter sort of their, we can then check on its status, and it's in a queue at the moment, but eventually the first 3 subjects will start running on different nodes at the same time. And it'll take maybe 10 minutes or so to run in this case, so a pretty non-intensive task. We've then built this carbon tracking script, CalcCarbon, and what that does is it has a bunch of global things at the top, like power use effectiveness and carbon intensity that we're feeding it. We've got the average carbon intensity for the UK. Then a bunch of functions where it's going to find information in the high-performance computing logs, put them into various formulas, and give us on the other end an estimate of energy use and carbon emissions on the other side that we can then access and work with. What that needs as well is another little file that contains, for each different processor type, how many CPUs does it have, and what thermal design power value does it have, which again is a measure of sort of heat wastage it's taken as a measure of sort of efficiency of the processor, as well as for each node on the system that we could access, which processor does it have. So we can use this information together to understand how efficient the hardware is that we're using for a given job. So what I'm doing now is going into the directory that contains my carbon tracking script. All I need to know now is the ID number of the job that we've run, which kind of we printed out earlier, and which would have I've got scripted to kind of save in a specific location. So once I'm in this folder, we can first run this qact command, which on this system basically just means for this job, give me all the log information for that job. And this is the information that will be accessed by the carbon tracking script in a sec. So again, that'll take a few seconds to run. And then for each of our 3 subjects, it will tell us a bunch of stuff, most of which will be irrelevant to us, but factors including exactly how long did the job take to run in seconds, what's the maximum memory usage it reached at any one point, what was the CPU time, how many cores did it use. And then we can take that command, that qact command, and kind of pipe it into our carbon tracking script, CalcCarbon. And this is me trying to remember if it's an uppercase or a lowercase c, I think, for this, for this pause. There we go. So once we've run that, it will generate an output file in a directory in the same location as the carbon tracking script, which for each subject has everything that we're interested in. And we can zoom in on that. Effectively, that includes the kind of the materials that it's used to make the estimations, like the number of CPU cores, the duration in seconds, CPU time overall, and then the energy usage and the estimated carbon emissions for both CPU and memory and overall. And that's it. That's how we get our carbon estimates. The benefit of these tools is that once they're set up to run like this, we don't need to know anything or do anything apart from kind of input our job ID number with that script. And the benefit is as well, they'll work for any tool. Unlike embedded tools, they'll work for anything that runs in the high performance computing cluster, basically, because all it needs is these logs, which are automatically saved out anyway. Again, the specific tool is going to become redundant pretty soon, but on the new Artemis system that's coming in, we'll have hopefully a new kind of carbon tracking dashboard that will be quite easy to use. And we'll be running some kind of example usages and demonstrations of that in the next year or so. So do keep an eye out for that. But we kind of view this as being the kind of gold standard at the moment of providing the most flexible and accurate and easy to use kind of carbon tracking methods. Okay. So we've got one last tool to go through. This is the climate aware task scheduler. Again, we're going to do some kind of hands-on use here. So we talked before about the carbon intensity of energy over time and how this kind of systematically varies. Because we can get live intensity data for the UK and we can get a forecast of the next 48 hours, what tools like this can do is take a snapshot and say, here is the best time in the next 48 hours to submit your job, where you'd use the minimum carbon you could possibly use in that window. You go to the GitHub page, which I'll put up the link again in the set once we're actually using it. But this is what it looks like. So some nice AI generated art. This is about some collaborators of ours. So we have another quick video here. This is the GitHub page you'll go to in a sec, and you can either kind of clone it directly onto your computer, or you can do what I did and download the whole repository there, the download button, which will just give you a directory containing the contents of the GitHub page. So we can extract that. And then that contains all the materials that we'll need to run this script. What I'm then going to do is just open up the command prompts in Windows on my laptop. We've tested this out on Mac as well, and it does work in Linux. And I'm going to Python call this package, cats. I'm going to tell it the job's going to run for a duration of 60 minutes, and the location is BN2 here in Brighton. And it will then tell us, if you submit your job now, you'd emit 179 grams of carbon for each kilowatt hour energy you use. Whereas if you waited until the optimal time, which is the following day at about 1 in the morning, it'd be about 85 grams. So about half the carbon basically for the same amount of energy. So that involves waiting about 14 hours in this case before the job would run. So that's the timestamp is generated there. The kind of the next logical step is we obviously don't want people waiting up until 1 in the morning to submit these jobs. We want to be able to tell the high performance computing cluster, I want you to take this job and submit it at this certain time. So all that I'm doing here is going back to the same directory we saw before, where I've got my FSL pre-processing script. Because again, I'm just going to be running that script. And separately in another window, I've got my optimum start time, this little code here. So now all I need to do is I want to submit this job at 2024 on May 17th at 20 to 1 in the morning, and then just give it the script name, FSL pre-proc. At that point, the job again goes into the queue like it did before, and you won't see this play out in real time here, but it now enters this queue waiting stage. It will stay there until that time at 1 in the morning, and then it will start running overnight. So as long as you don't have an urgent need to access this data, there's not going to be a downside to you really. It'll just be running in the background overnight. It'll be ready for you there in the morning. Yeah, so the scheduling, the actual scheduling is an interesting question. So you can run the time, you can get the timestamp on any computer where you can access this tool basically. Yeah. I think the start app thing is a Linux thing that would work, I think, on the Sussex Neuroscience interface as well. Windows and Mac may have equivalent kind of wait states. I don't know, to be honest. I can look into that. Okay, so now we'll see how this goes. We're going to have a quick test of everyone trying to run cats for themselves. And some of you may have seen the email beforehand. Maybe you set this up, maybe not. But the first step will just be going to the GitHub page for cats. You can go to this URL, or you can just type in climate aware task scheduler, or you can just go into your terminal and just do git clone and then the URL if you're more comfortable doing that. But yeah, you can also just go onto the GitHub, go to this code button, and then downloads it. It'll just give you a folder, basically. This is require Python being set up on your laptop as well. So you could just, if you're comfortable doing that now, you can just Google download Python if that's not already set up and get the version relevant for your system. Because that'll be needed to make this run. So I'll keep the URL on screen. Yep, they're at the top, so you can still go to that and download the package. But the basic process here is going to be just opening the command prompt on your computer, changing working directory into the folder that you just downloaded, where all these files are located, and then running this command. So Python and cats, and then the duration of your job in minutes, and the location of the computing, in this case, BN2. if you haven't run this before, you haven't downloaded these packages before, it may say that you're missing various tools. For me and Charlotte, both on Windows and Mac, we've been able to get it to work by installing these 4 modules, which you just do through pip installing in your command line there. So again, feel free to have a little play around with that. Yeah, just for the next 5 minutes or so, and then we'll come back. Okay, I know that it seems like pretty much everyone has had difficulty installing this. So sorry, this was a bit of a, yeah, we didn't know how this was going to work at scale. Basically, it seems like people are struggling to access some of the packages that it needs here. So I'm sorry about that. I think we didn't get it to work in real time. Hopefully, in the interest of time, we'll move on, so we're not keeping people late. But hopefully, the GitHub will have some more answers on this if there are specific issues that you're running into. But when it works, it should be great. And we're hoping to get this set up with the high performance cluster that will come in, the new kind of Artemis system, in which case it will be sort of directly integrated and people won't have to set it up themselves so much when running it. Just as some context, this is where it's grabbing the data from, this live carbon intensity API. So you can even go to this, even if you're not using cats, if you're looking to like start your dishwasher at the optimum time, you can go to this website and find this information sort of manually. So it'll show you what the average carbon intensity for the UK today is, what the highest point is going to be, and the lowest point by time of day, as well as over the next 2 days. Just out of interest, I'll see if I can grab this up. It will show you by region as well what carbon intensity is, which varies pretty wildly across the country. So the next thing I was going to ask you to do is sort of play around with the postcodes and then see how your optimum timestamps varied, because you can see that at the moment, where around where we are, we've got 194 grams for each kilowatt hour. Up in Scotland, where usage might be lower and renewable infrastructure is better, it's like nothing, like 10 grams. There are massive differences across the country there. So yeah, you can make use of this information basically when scheduling. Okay.
Thank you so much everyone for coming. We are going to be running a second workshop in the autumn once Artemis has been installed, and we've got some of these things up and running on Artemis. So do come on to our one in the autumn as well.
Thanks everyone.